Hi everyone, I'm Leslie and Danielle and I work at CEAList in France. Today I'm going to present the work I did with Sébastien Bardin and Tamara Rezk on how to efficiently verify constant time programs at binary level with relational symbolic execution. For the context, we want to protect the secrets manipulated by a program from an attacker that can monitor the execution time and execute on a shared architecture. The execution time can be influenced, first, by the control flow of the program, which means that a secret-dependent conditional can leak information about the secrets, and second, secret-dependent memory accesses can also leak information to the cache that can be recovered by an attacker via cache attacks. The constant time programming discipline is a countermeasure against timing attacks that is used in cryptographic implementations. Formally, constant time states that two executions with the same public input must have the same control flow and the same memory accesses regardless of the value of the secrets. And this ensures that the execution time is independent from the secrets. Unfortunately, constant time is generally not preserved by compilers. As an example, I put here a simple constant time selection function without secret-dependent conditionals. When I compile it with CLang and optimization level 0, it is compiled to a constant time binary code, still without secret-dependent conditionals. However, when I compile it with optimization level 03, the compiler recognizes the pattern and optimizes the code by introducing a secret-dependent conditional and breaks the property. Constant time is important to protect cryptographic implementations against timing attacks. However, writing constant time code is tricky, and the compiler may introduce violations. For this reason, we need automatic verification for constant time at binary level. Unfortunately, analyzing binaries is more difficult than analyzing higher level code, especially because we have to explicitly reason about the memory. A second challenge is that constant time is not a standard safety property, like for instance verifying the absence of buffer overflows. It is a two hypersafety property because it relates two executions of the program. For this reason, we need dedicated tools for analyzing pairs of executions. There are a lot of verification tools for constant time analysis. Some of them target high-level code, like source code or LLVM, and leave the gap open for violations introduced by the compiler. We might think that analyzing LLVM code is safe, but actually we show that violations can be introduced in the translation from LLVM to XLA6. And what about programs compiled with GCC? As for the tools that target binary code, they are either based on dynamic analysis, and they sacrifice bounded verification, which means that they cannot give any guarantee that a program is secure, or they make over-approximations and cannot report precise bugs. Our goal is to fill this hole and design an efficient bug-finding and bounded verification tool for constant time operating at binary level. Let me define right now what I mean by bug-finding and bounded verification. An analysis is correct for bug-finding if when it finds a bug, then there is a real bug in the program, meaning that it can report two concrete executions with the same public input, but with different control flow or different memory accesses. And an analysis is correct for bounded verification if when it reports that no violations are found up to a certain bound, then there is no violations in the program up to this bound. Bounded verification is well suited for verifying cryptographic implementations, because we can usually bound the analysis by bounding the size of the input, like the cryptographic keys. One of the best techniques we have for that is symbolic execution. Symbolic execution is widely used for bug finding, because it can report precise bugs and give counterexamples. And it can also be used for bounded verification. And last but not least, it scales well on binary code. In our paper, we adapt symbolic execution for constant time analysis at binary level, and we get bug finding, bounded verification, and scalability. Our approach builds on relational symbolic execution, which consists in executing two versions of the program in the same symbolic execution instance. However, we show that this technique does not scale on binary code. This is why we complement it with dedicated optimizations for binary level and constant time analysis. Our contributions are the following. First, we designed dedicated optimizations for relational symbolic execution at binary level, and we proved our analysis correct for bug finding and bounded verification. Second, we implemented our technique in the binary analysis platform Binsec and compared its performances with standard approaches. Then we performed large-scale experiments on cryptographic binaries. We gave new proofs at binary level for programs previously verified at a higher level, and we replayed non-bugs. Finally, we extended and automated a prior manual study on constant time preservation by compilers, and we discovered new bugs out of reach of tools for LLVM. The standard approach to adapt symbolic execution for constant time is to use self-composition. So here we have a program with public input and secret input. Symbolic execution consists in executing the program with symbolic inputs instead of concrete ones, and it will map each variable of the program to a formula over these symbolic inputs. For example, here the variable a maps to the symbolic value alpha. Note that because we are analyzing binary code, we also need a special memory variables that map to a symbolic array mu. The symbolic execution will produce a formula over our symbolic inputs, which represents an execution path of the program. For constant time analysis, when we arrive at a conditional statement or at a memory access, we have to check that it does not depend on the secret. For example, here, we want to check that this load A does not leak secrets. We can do that by building a formula representing two executions of the program with self-composition. We take the current formula, duplicate it, rename all the variables, put the original formula and its copy together, add the precondition that the public input are equal, and finally ask, can alpha be different from alpha prime? This self-composed formula can be sent to an SMT solver. If the solver returns that the formula is unsatisfiable, then it means that the load expression does not leak secrets. If the formula is satisfiable, the load expression depends on the secret and the solver returns a counterexample that triggers the vulnerability. The problem with self-composition is that it generates a lot of expensive insecurity queries at each conditional statement and each memory access. This is because it takes two executions with no sharing between them, and thus does not keep track of secret dependencies. We show in our experiments that symbolic execution for constant time using self-composition does not scale. A better approach is to use relational symbolic execution, which executes directly two versions of the program in the same symbolic execution instance and maximizes sharing between them. Because the public input is the same in both executions, it maps to a simple expression. On the other hand, because the secrets can be different, they are mapped to pairs of expressions. Note that the memory, because it initially contains secrets, is also mapped to a pair of symbolic arrays. Now, the symbolic execution gives us a formula representing two executions of the program with the same public input. In our example, we want to check that the expression load A does not leak secrets when A maps to a pair alpha prime. To do that, we take the current formula representing two executions and add, can alpha be different from alpha prime, and just send it to the solver like before. The interesting thing is that when A maps to a simple expression alpha, then it means by definition that it does not depend on the secret. And so in this case, we can spare an expensive query to the solver. This mechanism, together with good simplification rules, help us keep track of secret dependencies and reduce the number of calls to the solver, which drastically improves performance. The problem with this approach is that it does not work for binary analysis. The memory, which initially contains secrets, is duplicated and represented as a pair of symbolic arrays. As a result, all the load operations from this duplicated memory are also duplicated, and we no longer have sharing and precise secret tracking. So we end up duplicating everything and send insecurity queries to the solver. This is why we came up with a simplification for binary analysis. We called it FlyRow for on-the-fly read-overwrite. It is based on read-overwrite, which is a simplification for SMT formulas that simplify symbolic select operations from arrays. We adapted the simplification to build a memory model in our symbolic execution to simplify loads on the fly, avoiding to resort to the duplicated memory. I'll give here a simplified overview. This memory model is the history of store operations encountered during the symbolic execution. When we encounter a load operation, like load ESP-4, we can perform a lookup in our memory model to find the matching store at address ESP-4. And then we can directly return the corresponding value, here lambda, instead of returning a pair of symbolic select expressions from the duplicated memory. For this optimization to work, we need to be able to find matching indexes efficiently. This requires simplifications of symbolic expressions, which are detailed in the paper. We also designed two other optimizations dedicated for constant time. The first is untainting. When we ask the solver if a pair of expressions alpha alpha prime are distinct, and when it answers that they are actually the same, then we can replace pairs alpha alpha prime in the symbolic executions by the simple expression alpha. This allows us to track secret dependencies more precisely and spare additional insecurity queries. The second optimization is full packing. It gathers insecurity queries along a basic block and sends them to the solver all at the same time in a unified query. It reduces the number of queries, which is useful for constant time because there are a lot of insecurity queries. We implemented our analysis and performed an experimental evaluation to answer the following questions. First, is it effective? Can it find bugs and perform bounded verification on real-world cryptographic binaries? Second, how does it compare against standard relational symbolic execution? And third, is it generic enough to handle several architectures and compilers? And there are more in the paper. We assessed the effectiveness of our tool on a large number and variety of cryptographic binaries. We analyzed small utility functions like constant time selects from OpenSSL and HackleStar, but we also analyzed larger cryptographic primitives taken from multiple libraries. 296 of these programs were constant time secure, and we were able to perform exhaustive bounded verification for all of them, meaning that for a fixed size input we explored all the paths and found no vulnerabilities. This represents a total of 23 million unrolled instructions, analyzed in less than 1 hour. And this is the first automatic constant-time analysis of these programs at binary level. And we were also able to find vulnerabilities introduced by the compiler in binary compiled from constant-time sources, including vulnerabilities that slip through prior analysis. I'll say more on this point later. Next, to assess the scalability of our technique, we compared our analysis against standard relational symbolic execution, so without our dedicated optimizations. On our experiments, we were 700 times faster than standard relational symbolic execution in terms of instruction per seconds. More important, our optimizations are necessary to analyze large programs without timing out, and we were able to fully explore 14 more programs than relational symbolic execution. Finally, we automated a manual study on constant time preservation by compilers, and we extended it in several ways. We added new functions, the GCC compiler, a new version of CLang, and ARM binaries. Interestingly, we found that GCC, with optimization level 0 can introduce bugs in constant time programs. However, it tends to remove bugs as optimization level increases, contrary to CLang. We also found that CLang can introduce violations in the translation from LLVM to x86 that cannot be caught by constant time verification tools for LLVM. This shows the importance of reasoning directly on the binary. And you can find more of these fun facts in the paper. To conclude, we presented how to efficiently perform bug finding and bounded verification for constant time at binary level. We do not make approximation, but we scale by maximizing sharing between pairs of executions. And because we target binary code, we do not rely on the compiler to preserve the property. Finally, we made an experimental evaluation on a large set of cryptographic binaries and gave new proofs at binary level, found new bugs, and automated a manual study on constant time preservation by compilers. Thank you very much for your attention.